About valence bond theory. Valence bond theory. In this, I'm going to talk about orbital orbital overlap orbital overlap concept I am going to discuss about. VBT theory was proposed by two scientists, Hitler and London. Hitler and London, two scientists proposed this valence bond orbital theory, and it was modified, further developed by Pauling scientist, Pauling and Slater, two scientists. They modified in 1931 this valence bond theory. The valence bond theory purely explains the formation of covalent bond in terms of energy, and also the valence bond theory explain the directional property of covalent bond we say, whereas ionic bond having not directional property, the covalent bond has the directional property we say, like the covalent molecules are linear in shape, pyramidal in shape, and trigonal planar. So trigonal planar in shape. So these are due to directional properties of the bond we say. So the valence bond theory, so proposed by Hitler and London scientists. It was modified by Pauling and Slater 1931. So this valence bond theory purely explain the formation of covalent bond in terms of energy changes, and also the valence bond theory explain the directional properties of the covalent bond. So why some molecules are linear in shape, why some molecules are pyramidal in shape, why some molecules are trigonal planar. So we'll explain in detail, we'll discuss in detail about this directional properties of covalent bond. The valence bond, the orbital overlap concept, purely focuses on overlap of pure orbitals when two atoms combine. So how these orbitals overlap? As you know that when two atoms combine, their orbitals, particularly valence orbitals containing unpaired electrons. The valence orbitals containing unpaired electrons, when undergo interpenetration interpenetration. So valence orbitals containing unpaired electrons. When two atoms, so or when these valence orbitals undergo interpenetration, there are three types of orbitals overlap. So are possible. Number one is positive orbital overlap. Number two is negative orbital overlap. Number three, third one is the possibility is zero orbital overlap possibilities are there. That means when two atoms combine, so whenever two atoms combine, their orbitals, atomic orbitals also subject to undergo interpenetration. As a result of this, there are three types of orbitals overlap is possible. Due to this, three types of orbitals overlap possibility. So we can see two kinds of bonds are possible. One is sigma covalent bond. Number two is pi bonds are possible. Two types of bonds are possible. One is sigma, other one is pi bonds are possible. Let us discuss. So what are these three types of orbitals overlap concept? Let us discuss now. As I mentioned here, the number one is positive orbital overlap. So what is this positive orbital overlap? So generally the positive is the word indicate probability of the electron in particular direction. For example, if I take s orbital, the probability of electron for the s orbital in all the directions, you say, means towards, if you consider towards x-axis positive, and so other side will be the negative. So this is y-axis, this is x-axis. So in what direction the probability of the electron is taken, that is a positive probability of electron. So, and if you consider the s orbital spherical, as you know that s orbital is a spherical, and the probability density, this side I'm taking positive, and if the electron exists this side, other side will be the negative, we say. Similarly, if another s orbital, if you take, so this is the positive direction, positive side, this is the negative side. So whenever two hydrogen atoms or two atoms containing s orbitals approach each other, so these atoms are lying on internuclear axis, and the positive side of the s orbital overlapping with the positive side of another s orbital, so resulting positive orbital overlap, and resulting end on end, that is what we say s overlapping, s orbital overlap, we write overlap, ss overlap. So resulting, now you see, when this s orbital overlapping, another s orbital overlapping, so resulting the sigma bond formation. This is their nucleus, their nuclei are lying on internuclear axis. So the bond is resulted here. So end on end overlap. So this can result. So positive orbital overlap. The extent of overlap is more, the stronger is the sigma bond, we say. If you consider p orbital, as you know that the p orbital, there are three types of p orbitals. P orbitals are three types. Number one is px, py, and pz. The probability density, see, what are the shapes of these p orbitals? Dumbbell shape. Dumbbell shapes, we write. If you find the probability density of the electron in the x-axis direction, this direction, x-axis direction, this is a px. And if you find the probability density of the electron towards y-axis, this is py. And if you find the probability density of the electron towards z-axis, that is pz, we say. So this is the positive, this is the negative, this is the positive, this is the negative, and here is the negative. So the probability finding of electron, so taken as positive and zero negative, we say. Here in among the p orbital, the positive overlap will be, let us see. So now let us see the positive. Consider px overlap, px orbital. This is the positive side plus another px orbital. Positive means when two atoms containing, so px and px orbitals, so combining the positive side of, so positive side of one orbital combined with the positive side of another and on an overlap, resulting, that is pp positive overlap, we say. Positive overlap is there. Then a bond is possible, sigma bond is possible, we say. So the resultant structure will be, here is negative, here is the positive, here is the positive. So positive overlap between the two p orbitals of atoms, resulting sigma bond. So sigma bond is possible on the internuclear axis, on the internuclear axis. Sigma bond is possible, which is stronger bond. The second case, if you consider the orbital px orbital, positive side is other side, this is negative end, plus another px orbital, negative end, positive end. So if two p orbitals overlapping in the direction of negative ends, so no bond is possible. No bond is possible. Bonding is not possible because both orbitals are overlapping negative ends where the probability of electrons are zero, we say. And so this kind of bond is not possible. And another case, if you take px orbital positive direction and px orbital negative, one is a positive, other one is negative, also no bond is possible. This is what we call negative orbital overlap idea. And if you consider, so orbitals, p orbitals, so lying in the direction of y-axis direction, this is py, this is py, and so these orbitals are perpendicularly perpendicularly lying on the internuclear axis, internuclear axis. These two orbitals are their positive ends like this. Their positive ends. So here these two py orbitals of different atoms, when they come closer, only possibility of overlapping is side-on-side overlap. Side-on-side overlap is so possible since these orbitals are perpendicular to the internuclear axis. So of the two atoms, nuclei of two atoms, we say. As a result of this, so what kind of covalent bond is possible? Pi bond is possible. Pi bond is possible, which is a weak bond as you compare with the sigma bond. Weak bond is possible. This is positive overlap of p orbitals lying on perpendicular to internuclear axis. There is another possibility of there is a pz orbital is present. Another one is pz orbital also present. Their positive ends. These are so also perpendicular to their internuclear axis. And when the two different atoms having these pz orbitals with the same energy overlap and resulting pi bond pi bond we say is possible. And among the p orbitals there is negative orbital overlap orbitals also possible. So one side positive probability, second other side is negative, so bond is not possible here. Or so two negative orbitals orienting, also bonding is not possible, we say. That means if the orbitals approaching negative ends, so what does it mean? So probability density of electrons not there and bonding is not possible. That means the orbitals, valence orbitals should have at least one unpaired electron for the bond formation. So these are the three types of orbitals overlap. And finally, from this, how many types of orbitals overlap are possible means there is number one, SS overlap, number two, SP overlap, number three, PP overlap orbitals are possible. So there are three kinds of orbitals overlap. One is SS, SP, and PP overlap, we say. So these overlaps will give rise two types of covalent bonds. One is sigma, another one is pi bond. Let us discuss example for each SS orbital overlap bond formation, SP orbital overlap bond formation, PP overlap. Now let us take SS. So SS type of overlap only possible in hydrogen molecule. So one hydrogen atom combine with another hydrogen atom to form H2 molecule. As you know that each hydrogen atom electronic configuration is 1s1, 1s1, and H2 molecule is 1s2. Each hydrogen atom containing single electron, that electron is present in s orbital. Each hydrogen atom containing one s orbital in that each, so unpaired electron is present. As you know that the s orbital is spherical in shape. Assume that here is the electron, one unpaired electron. Then there is another hydrogen atom also having 1s1 configuration. It has the nucleus, and here is the electron. So electron is present. Two hydrogen atoms having unpaired electron each. So unpaired electron each, we say when two hydrogen atoms combine, there is interpretation of two s orbitals will take place. As a result of this, these unpaired electrons are paired. Their energy is lowered. Energy is lowered, we say. So when the electrons are paired, energy of the molecule is H2 molecule energy is lowered. And here is the nucleus of A atom. Here is the nucleus of another atom, we say. So these electron pair, one electron pair that is formed due to the interpretation of two ss orbitals lying on internuclear axis at equidistant superposition, and H2 molecule is formed due to combining of two s orbitals and resulting sigma bond we say. So this is example for, since when two hydrogen atoms combining, two s orbitals are overlapping, then it is said to be SS overlap, we call. So resulting sigma bond, so between two hydrogen atoms, the sigma bond between the hydrogen atoms will be, we can write HH is the sigma bond, we say. That means two hydrogen atoms sharing one pair of electron, one shared pair of electron between them, resulting SS overlap. Similarly, you can think in which molecules this SS overlap is present, you can think. And next type of overlap of atomic orbitals overlap is sp orbital overlap, we say. Now, let us discuss second type of orbital overlap is sp overlap. For this, we take example of which molecule. One atom should have s orbital, another atom should have p orbital in the valence shell. Now, for understanding of this sp orbital overlap, I'm taking, so one atom is hydrogen that containing one s orbital, and other atom is the chlorine to form HCl, where the electronic configuration of hydrogen is 1s1, and where the electronic configuration of chlorine is chlorine, and chlorine outermost electron is 3s2, 3p5. So according to the valence bond theory, only orbitals having unpaired electrons will combine, whereas the orbital having paired electrons, paired electrons doesn't take part. Now, as per the valence bond theory, s orbital having unpaired electron, it can take part, whereas that 3p orbitals are divided into 3px2, 3py2, 3pz1. So out of this 3p orbital having unpaired electron, This orbital take part in the bonding when chlorine combine with the hydrogen. That means here the overlapping happens between p orbital of chlorine with the s orbital of hydrogen. Now, this is the hydrogen atom, s orbital. Here is the nucleus. Here is the electron is present. This is 1s1 plus the chlorine atom containing 3pz. 3pz orbital, I am taking this direction. This is the 3pz. So where the electron is present here, other side electron is not present, this side electron is present. This is the, so chlorine 3pz orbital. I am not representing 3py, 3px or 3s orbitals. Only I am taking 3pz orbital. So, and I am representing only, so 3pzr. This is 3pz orbital, 3p1 of chlorine. So approaching, when the chlorine atom approaching the hydrogen atom with 1s and the 3p orbitals, so what happened? It can result to, so this s orbital of hydrogen and p orbital of 3pz. So 3pz1 and 1s1 overlapping, resulting sigma bond, we say. And between these hydrogen and chlorine, this electron pair is formed. So unpaired electrons are paired here. Then energy, when electrons are paired, energy is lowered. Energy is lowered, then molecule is stable, we say. Here is the nucleus, and here will be the nucleus. Both atoms are stabilized by forming. So the molecule is hydrogen, chloride, HCl, and hydrogen and chlorine sharing one electron pair, resulting one sigma bond, because this is end-on-end overlap. So because this end-on-end overlap, so resulting, what is that mean? Sigma bond. So this is example for sp overlap of orbitals. sp overlap. Similarly, sp overlap is possible in HF and HBr and in HI. So molecules, this sp orbitals overlap is possible. Let us discuss one more pp type of overlap. Now, the third type of orbital overlap is that, so p orbital overlap. pp orbital overlap is same. So mostly this type of orbital overlap is possible among Cl2 molecule, O2 molecule, and N2 molecules, we say. Let us consider, so one chlorine atom approaches another chlorine atom will form Cl2 molecule. As you know that, so each chlorine atom electronic configuration is chlorine, so 17 is the atomic number. So outermost electronic configuration, valence shell electronic configuration is 3s2 3p5. And under chlorine also 3s2 3p5 is the electronic configuration. And if you observe, 3s2 is completely filled, 3p5, so 3px2 completely filled, 3py is also completely filled, and 3pz is having one unpaired electron. That means, so each chlorine atom only having, so 3pz only having unpaired electron. These orbital only so participate in chemical bonding. Here is the 3pz1 of another chlorine atom. Here is, So this is a chlorine B atom. This is chlorine A atom having their respective 3pz1 electrons. When two chlorine atoms approaches, so these 3pz orbitals overlap by what kind of overlap? It could be, this is end-on-end overlap resulting forming the, so unpaired electrons will pair up here forming the sigma bond. The sigma bond is a stronger one between the two chlorine atoms when their two orbitals. See, you can draw the structure of the chlorine atom here. Chlorine atom like this. Another chlorine atom also we can make. Here is the chlorine atom. So between the two chlorine atoms, so chlorine atom, there is a sigma bond is formed. And this sigma bond is due to, so due to end on overlap of orbitals, resulting sigma bond, which is a stronger bond, we say, which is a stronger bond. So this is what we call pp orbital overlap in Cl2 molecule. And if you consider O2 molecule, so let us see.